Hi, I'm Nikhil Sakthirajan, and this is my research into the novel implementation of a grip manipulation and haptic feedback system into a prosthetic arm. So to introduce my topic, why grip manipulation? Grip manipulation is necessary for tasks of daily living because let's say you're holding like a pencil, right? Or pen, you're going to need to only adjust a few fingers. Everything else can be opened or closed, right? You only adjust a few fingers. It'll be like a looser grip, and you're not going to be able to you're not going to use all your fingers in holding it. Otherwise, you're not going to be able to write properly. Versus when you hold like a water bottle or my phone, I'm going to use all of my fingers. All my fingers would be gripped separately and individually, like in a different way. So it's easier to hold it. And I wouldn't even make it that tight. I'd only make my grip a bit loose, so it's easier to hold it and it's easier to use it because you need that type of grip so you're able to functionally live daily life. And studies have found that this significantly improves user control over the prosthetic. And then additionally, why haptic feedback? Haptic feedback is necessary because it provides tactile cues necessary for grip and object manipulation. When I touch a calculator, I know that it's a harder object and I don't need to have to put some pressure on it to hold it. Otherwise, when I'm holding like a glove or like a piece of cloth, I know it's like a softer object. I know how much force I need to put on it to hold on it. It's done using microreceptors in the skin, but common prosthetics do not provide like that type of tactile feedback, which makes it hard for people to use it to use their common prosthetics. Current solutions for grip manipulation. So currently we have EMG or electromyography, which measures electrical signals generated by muscle movement. And essentially, you'll have like an electrode placed on a muscle and it detects like the contraction or if you flex it, and it'll convert that to an electrical signal that you could translate into movement in the hand. However, because you're going to be measuring the signal of the muscle, like as a whole, you're not going to know like which individual fingers you want to move unless you have a very advanced and precise EMG system, which means that current commonly used types of EMG are ineffective because it will only open and close the prosthetic. It won't specifically map your finger movements, which means that it's difficult for the user to make those precise grip adjustments that I mentioned before. Because let's say you want to hold the pencil, you're only going to really be able to hold it with all fingers or with like a few fingers versus when I'm holding my phone. Additionally, these advanced EMG systems are expensive and complex to code because of how you have to define which signals to pick up on and which ones to not, because there would also be electrical noise from other components of the prosthetic. Current solutions for haptic feedback use ineffective piezoelectric sensors. Piezoelectric sensors, or based on the piezoelectric effect, basically works as this. You have these pads, and when you push down on an electrical signal is generated, and then you can base these signals. These signals are different based on the pressure applied on the plates, and then you translate those electrical signals to a reading for the haptic motor. And then these are not accurate because there's a slight delay with the piezoelectric sensors, which means that your haptic feedback system is not going to be accurate enough for you to make really complex adjustments, and that leads to its ineffectiveness. So the problem, prosthetic technologies are too expensive and are ineffective. My hypothesis is that the research will prove that the additions of a low-cost grip manipulation system and haptic feedback system would significantly improve control and dexterity over the prosthetic. Methodology. So for the prosthetic design, it's designed and constructed using a bamboo P1P3D printer. It's a modified version of the open source InMove robotic arm, which is used for just a robot that would stand in your room, and it's the arm from that. I modified it and made the inside a lot different because it was easier for me to route cables, and I made it more different part. I separated the palm in a different way, so it's easier for me to construct, and 3D print. And then this is done, the entire prosthetic is controlled using a tendon-driven mechanism where we have servos mounted in the forearm which turn fishing wire that acts as tendons. And then you have a few pictures of the tendon-driven mechanism. In addition, we have this video where you could see the servos turn, and then that turns the hand. I'll give you a few seconds to look at it. Great. So for assembly, we have this is done on a non-functioning version of my hand, which I used for a separate project, but this is the same version of construction where we have the fingers are individually put on, and then you wire it, and then you have the different parts of the palm which you put in, and then you can finally assemble it all and then have the wire routed through the palm which goes to the forearm. For the control system, this is done using a leader-follower system where the prosthetic mimics the movement of the hand. This is done using flex sensors and force sensors. So with flex sensors, when you bend it, the resistance changes across the board, and this translates to movement with the servo. Force sensors, on the other hand, have pressure applied to them, and then it changes the resistance of the sensor, and then you're able to translate that change in resistance to vibrations on the haptic motor. To add on to the flex sensor point, flex sensors you bend, right? And then you have the electrical signal generated. Basically, you would place the flex sensor on the hand, and as you bend it, that electrical signal is generated, and then you're able to generate movement within the prosthetic. So this entire circuit is done on an Arduino Mega microcontroller, which is this really fancy microcontroller with multiple ports. We used an Arduino Mega versus the commonly used Arduino Uno because we needed more ports to fit all the sensors on. So this is done with two circuits, one for the prosthetic and one for the control glove. The prosthetic circuit utilizes just servos and the force sensors, while we have the control glove which uses the flex sensors and haptic motors, and this kind of feedback is relayed through the Arduino. And we have a GIF on the bottom right corner which demonstrates the force sensors. So for the glove design, we have these flex sensors which are pictured in the picture right here, and you can see they're stitched and taped onto a tight-fitting glove, so you're getting accurate finger movements. And then haptic motors are placed inside of the finger, stitched inside, so you're able to feel it, and it's easier to understand what type of object you're holding. For testing, we had 3 tests. The first test, we had to evaluate the gripping ability. So the prosthetic would grip different objects for a certain duration. Objects would range from everyday objects like a screwdriver to unconventional objects that require 3D printing. As you can see, we were able to successfully hold a few objects, which I'll go more into the result. We also have the tactile feedback, where we'll have the user and the prosthetic grip different objects, and then we want to test whether the force the user uses on the object should match the intensity of the haptic feedback. Additionally, I'll blindfold the tester and have them hold objects with the prosthetic and test whether the user can feel the object the prosthetic is holding using the haptic feedback. So for this test, we actually mounted additional force sensors onto the glove for this short test, where we would see that the force was matching up with the force the prosthetic was giving, so that the haptic feedback was accurate. And if we're bored to evaluate the addition of both systems to make sure that the haptic feedback was a very beneficial thing, we would have it grasp more difficult objects such as a squishy water bottle, which would mean that you would have to adjust your grip accordingly because of how the water bottle will change its density because of its squishy nature. So for our results, test 1, we found the prosthetic was able to grip all objects for a given amount of time. In the case of the water bottle, the water bottle would start to slip as you angle the prosthetic more, because you're unable to tell how much force you're putting on the water bottle. For test 2, haptic feedback was found to be accurate to the force reading, and the user is able to feel objects using the feedback. For test 3, on the first run, we basically gave a time limit of 180 seconds, and we wanted to see whether the prosthetic would be able to hold the object for the given amount of time. And if the object would start to slip from the hand of the prosthetic, that's when we would cut the timer, even if it was holding it. But if it would slip a few inches but still being gripped on, we would count that as not being counted and we would end the timer, because in real life you're not going to be able to use an object if you're only holding it with like 2 fingers. Let's say you have the water bottle and that's only, if that's slipped down like 2 fingers, you're not going to be able to drink it. So for the first run, the prosthetic was able to grip some objects, and it was harder for the user to adjust their finger positioning on the control glove because there was no haptic feedback. And on the second run, we were able to grasp all objects because it was easier to manipulate grip, as haptic feedback told the user how tight the grip was. And you can see there was a large increase on average for the second trial and the first trial, because the first trial is pictured in blue and the second trial is pictured in red. So in conclusion, in context of the other work done, the results demonstrate that the expensive control algorithms are not required for improving prosthetic control. This inexpensive control scheme performed very excellent compared to other work, which is from the citations. This work can be used to create low-cost and highly effective prosthetics for a wider audience, because currently prosthetics range from $5,000 to $10,000 and can reach as far as $100,000 depending on what features you put on it. The total price of this project was $300 and performed very well. To improve my work, I would like to implement a wireless function for the glove and prosthetic to test whether wireless function can hinder or improve the functionality of it. We also want to implement dual force feedback, which would adjust the prosthesis position based on the force reading from the control glove and the prosthetic, which for this we'd have to implement a PID control so that the prosthetic is able to run smoothly. And I would like to add more joints to the prosthetic design to increase its dexterity and movement. And these are my citations. Thank you for watching.